Thanks, John. And I would like to thank the organizers for this wonderful conference we're having and for the opportunity to speak at it. If anybody is interested in getting these slides to follow along, you could go to my website and that will direct you to them. But yeah, indeed. So today I'd like to talk about pushforward monads, and this is a construction that was, I think, first appeared in the Formal Theory of Monads by Ross Street. And without further ado, let me tell you what it is. So it's a way of transporting a monad from a category to another along a functor. And in a nutshell, it's given by this construction here. So if I call my functor G and I'm my monad T on the domain category, then the push forward of T along G is going to be this right-hand extension of GT along G. Now it's not immediately obvious, but this has a monad structure when it exists, and that's what I'm going to call a push forward. So today I was going to talk about the construction because I feel like it hasn't received much attention in the past. And specifically I want to focus on two examples of this construction. The first one's going to be the push forward of finite power set monad on fit set to all sets. And then we're going to talk a bit about this one from field to set. Right, so let me begin by telling you about the general construction. Right, so I'm going to use the same notation as I did 2 slides ago. Now, pushforward monads answer this basic question of how can we transport a monad along a functor. And if you think about it, there's already a very well-known answer to this, and that's when G is a right adjoint. If we have an adjunction with F being left adjoint to T, then GTF is a monad on D, and this is very well known, it's classical. The most well-known example of this is when you start with the identity monad, you get the monad induced by the adjunction. But as was pointed out by Street in the Formal Theory of Monads, you could instead take this right-hand extension here, and if it exists, we'll get a monad on D. So let me explain how this monad is going to come about. Here's the sort of diagram for the kind extension. Yeah, so I think the most beautiful way of seeing why this is a monad is by constructing a sort of auxiliary category, which I'm going to call KGT, and it's really going to be a comma category, but let me say it explicitly. So its objects are going to be squares like this of a functor S, an endofunctor of D, and a natural transformation here. Anamorphism is going to be a natural transformation between these functors on the right that sort of intertwines the things in the square. Now what am I going to do with this category? Well, so far I haven't assumed that T is a monad. If I assume T is a monad, then I can give it a strict monoidal structure, and that can be done using the multiplication and the unit. And I guess quickly here, this is what the monoidal product of S and S prime would be. I put the two squares together. Of course, I don't have functor to T yet, natural transformation to T yet, but I can use the monad multiplication to get me one. And similarly for the unit of this new monoidal category. Okay, so now I have a monoidal category. The right-hand extension of GT along G, if it exists, is precisely the terminal object of this monoidal category. And as any terminal object in the monoidal category, it has a unique monad structure. And well, this is not quite the category, the monoidal category of endofunctors of D, but there's certainly a forgetful functor from this one to that one. And so that monad structure gives me a monad structure on this right-hand extension. So just as a sanity check that this is the right thing, let's see what happens if we start with a right adjoint, and do we get the well-known answer? The answer is yes, and that's a very simple check. It's because when you right-hand extend along a right adjoint, you just precompose with the left adjoint, so you indeed get GTF as before. One particular example of pushforward monads is codensity monads, which are perhaps better known. It's when you push forward the identity monad. And I can give you plenty of examples of codensity monads that have been studied, and here are some of them that I think are interesting. So the most famous one is the codensity monad of the functor that is the inclusion of finite sets into set. This is a result by Kennison and Gildenhouse from the 70s. It tells us that the codensity monad of this functor is the ultrafilter monad. So it sends a set to the set of ultrafilters on its power set. And even very surprisingly, the algebras for this monad are compact Hausdorff spaces. And so this highlights how the non-triviality of this process of pushing forward, because we just started with this functor, and we applied this general categorical construction, and we ended up with a theory of compact Hausdorff spaces. Two more examples of a similar flavor are if you take the inclusion of finite dimensional k-vector spaces into all k-vector spaces, its codensity monad is the double dualization, and its algebras are something called linearly compact vector spaces. And then one last example of a similar vein is if we take the inclusion of the category of finite groups into the category of groups, its codensity monad is profinite completion, and its algebras are profinite groups. So in all of these cases, there's these sort of examples of something finite including into something bigger, and we get codensity monads whose algebras are in some sense topological. Before I go into our new examples of pushforward monads, let me tell you about the universal property that they satisfy. So quickly, using this, the comparison natural transformation of the right-hand extension, I can cook up a functor, k up here, that's going to make this diagram commute, and so it's going to, every algebra for the original monad is going to be canonically an algebra for the push-forward monad along G. Hence I can see this functor k as a narrowing cut over D. Maybe you can see where this is going. So there's a well-known functor that takes a monad and produces a category over the category that the monad is on. And I'm going to call that functor algebra. It just sends the monad to the category of algebras. And then the universal property satisfied by this push forward is that k here is a universal arrow from this composite functor here to the function that sends the monad to its category of algebras. Let me say that a bit more explicitly. So it says that I have an isomorphism like this, natural in S. So every time I have a functor over D between this GUT to a monadic functor, so the forget functor from a category of algebras, I get a map of monads going the other way to the push forward. And so the nice thing about this is it gives us this motto that the forget functor for the push forward monad is the universal monadic replacement of this GUT. And one quick corollary of this is if you just change your monad to be, say in this sentence, you change the monad T to be the identity monad and change the functor to be GUT, then what you get is that that same universal property is satisfied by the codensity monad of GUT. And so really not only are codensity monads a special case of push forwards, but actually the other way around as well. Okay. So that's all I want to say about the general case. This is all sort of part of the formal theory of monads. And now I want to talk about some examples of these push forwards. In the spirit of the ultrafilter monad that I talked about, I'm going to be looking at pushing forward monads from finite sets to sets. So let me introduce what those monads are going to be. Something funny happens here, and that's that every monad on finite sets is really the restriction of a monad on sets. I guess a quick way of saying, checking that is just take the push forward, and when you restrict it, you get the same monad. So really, we don't have that many monads to work with, and these are the three, but I guess most straightforward monads I can think of in the category of sets that do restrict to finite sets. Just quickly, it's if I have a finite set E, I can take the plus E monad, whose algebras are E-pointed sets. If I have a finite monoid M, they can take the free M set monad. Because M is finite, this also restricts to finite sets. And then lastly, the power set monad on set. Again, the power set of a finite set is finite, so all of these restrict to finite sets. And I'm just going to be calling these restricted monads by the same name, except I have an F on top. So, okay, let's see what the push forward of these monads are when we go to set and what their algebras are. So, two hints as to how to answer this question are the following. So the unit of a monad is always a map of monads from the identity to the monad itself. And this push forward construction, when it exists for like both sides of a map of monads, it is functorial. So this gives us a map of monads from the push forward of the unit of the identity to the push forward of the monad. And if you remember, that's one of the examples I said before. This here is the codensity monad of the inclusion, which is the ultrafilter monad. So that's one thing. The other one is that because these monads were originally restrictions of monads on set, I can sort of use the universal property of this right-hand extension to give me a map of monads from the original monad to the push forward of the restricted one. And so these are a map of monads, and they give me forgetful functors in the opposite direction between categories of algebras. So what this is telling us is that whatever the algebras for the push forward monad are going to be, they're going to have an underlying T algebra structure, and they're going to have an underlying compact half-shift topology. And those two are going to be compatible in some way that is for us to determine. The first two cases are not very exciting, so I'll go through them a little quicker. So it turns out that, so let me remind you, P is the plus E monad, AM is the times M monad for M of finite monoid. The ultrafilter monad preserves finite coproducts. And so that you can use that to get isomorphisms here. In fact, these isomorphisms are distributive laws. And if you haven't seen the distributive laws that are isomorphisms before, that means that their inverse is also a distributive law. Okay, in any case, this makes these composite monads monads on set, and their algebras are rightfully going to have an underlying PE algebra or AM algebra structure and an underlying compact half-shift topology. So it seems like they're the right sort of thing to the algebras for the push forward, and indeed they are. So it's not a hard thing to prove, but this gives us our first example of monads pushed across I. The other example is a little more interesting. So there is one well-known monad on sets that also restricts to the power set monad of finite sets, and that's the filter monad, which sends a set to the set of filters on its power set. Because it restricts to this power set on finite sets, we again get a map of monads like this, and the interesting thing here is that actually this is the monad that you get by pushing forward the power set monad on finite sets to all sets. We have a map here, and we just need to show that this is an isomorphism of monads. I'll give you like a brief idea of how you can do that. So it's going to involve I guess finite sets is small, set is complete, so these are going to be pointwise scan extensions, and they're going to be given by this limit. So if I take an element of this push forward monad evaluated as a set X, it's going to be an element of this limit. And so for each function from X to a finite set, it's going to give me an element of the power set of the finite set. And the way I'm going to use that to build a filter on X is that I'm going to take the characteristic function of a subset and then build a filter F using this definition here. And then you can go through the checks, and actually this gives you an inverse for that canonical map of monads there. This is interesting in the sense that just like for the ultrafilter monad, we just started with finite sets and we go to compact half-shift spaces. Well, in this case, the algebras for this filter monad are continuous lattices, which are, well, either you knew it before or you know it now because it's this push-forward monad. They are a certain kind of complete lattices with a compatible half-shift topology. Now, the cool thing here is that the definition of a continuous lattice is not straightforward, if you've seen it before. But we get it here naturally from just the power set function on finite sets and the inclusion of finite sets in set. Okay, and then one last example. It's going to be the codensity monad of the inclusion of fields into rings, and we also look at the forgetful functor of a field set. Now, this monad has been known for a while. I'm going to call it K. This is interesting because the forgetful functor from field to ring or from field to set is clearly not monadic because field doesn't have products. And so if we answer what this monad is, we're answering what is the monadic replacement of this forgetful functor. So what is the monadic replacement of the category of fields over ring or over set? Let's quickly look at what the formula for the monad is. Again, it's going to be a pointwise right-hand extension. So for every map from a ring into a field, I'm going to get an element of that field in a way that's natural. Now, something interesting happens here. Every time you have a map from a ring to a field, it factors uniquely through one of these residue fields at a prime, namely the prime who is the kernel of that map. So in other words, this common category that indexes the limit here has a set of connected components indexed by the primes, and each component has an initial object, which is this residue field. So that's the long way of saying that this monad evaluated at a ring R is going to be split into this product of residue fields. Now, let's understand a little bit about what the monad structure is going to be. The unit, I like to say, embodies the philosophy of algebraic geometry, which is a very bold claim, but let's see why. It's because it takes an element of your ring and it realizes it as an element of this other ring, but this other ring is really just a ring of functions on the spectrum of the ring. Of course, each function is going to land in a different codomain, but that's how it is in algebraic geometry. For the multiplication, we would need to understand what k squared is, and for that I need to understand what the prime ideals of this ring are. But it is sort of a classical result that the prime ideals of a product of fields are in bijection with the ultrafilters on the indexing set. And moreover, all primes are maximal. So that allows me to say what the multiplication is, and it's sort of the projection onto those components which correspond to principal ultrafilters. Okay, so let's see what the category of k-algebras might be. Again, two hints. First one is that we were really looking at the forgetful algebra fields to ring, so every k-algebra is going to have every field is going to be canonically a k-algebra. So that's the first hint. Second one is because a ring is complete, and this category is monadic of a ring, it's also complete. So it's going to have all fields, and it's going to have all limits of fields in some sense. Field doesn't have a limit, as I said, it doesn't have products, but actually it turns out that that's all it's missing, in the following sense. The category of algebras for this codensity monad is the free product completion of the category of fields. And the way I prove this is sort of a bit nitty-gritty, but essentially the k-algebra axioms and a description of the unit and the multiplication you can use to show that every k-algebra, the underlying ring of it, is a product of fields, and then you can show that every product of fields has a unique k-algebra structure. And so that gives this result. But we don't need to stop there, because we have a monadic over ring. Let's do it over set as well. And so what we'll be looking at will be this monad induced by this Compostela junction, which is because you are as a right-hand joint, you can show that the push forward of k is actually going to just give you the codensity monad of the forgetful functor from field to set. And so again, this is going to be the monadic over set replacement of the category of fields. And so we're not far from knowing, so a little lemma is that per field has, and this forgetful functor preserves reflexive co-equalizers, and then you use the crude monadicity theorem to show the following. That product of fields is monadic over set, that the corresponding monad is the codensity monad of the forgetful functor. Now, I came across this result as sort of like I was very interested in this example, and I came out and I proved it, and then I realized that actually this was known, just not very well known. So actually this result of monadicity over set is already approved by Kennison and Gildenhouse. And yeah, although they use quite different, thanks. But my proof is sort of more explicit, and it really just applies to field.
The codensity monad field set, is it possible to say what that is?
Right.
Sorry.
You mean the monad as a functor? Or?
The theorem describes it as the codensity monad. What is that codensity monad? Was that something you described earlier? Yes, sorry. Maybe
I said it too quickly, but it's going to be the monad induced by this adjunction. I mean, not by definition, but it is. So it's sort of, you just get a set, you take the free ring in it, then you take this product over all the primes ideals of that, of the residue fields, And that's a monad.
Yeah, no, so I can see the technical definition. It's just like, what does it correspond? Don't worry about it.
Yeah, okay, sorry. Right, I mean, okay, so the meaning of this really is that if you, the theory of products of fields is the smallest algebraic over set theory that contains the theory of fields. And just to end, I would like to say that this is quite an interesting theory, so it doesn't have rank, for example, and there are like some funny operations. For example, there's an operation that detects algebraically independent elements of the prime subfield. And just because I need to end quickly, let me just end with this. So this is still sort of work in progress, and there's a lot of things I'm interested in that I haven't figured out yet. In particular, I think right now this is what I want to focus on, which is the relation between push-forwards and distributive laws, which is sort of, if you remember the section about finite sets and sets, all these monads looked like they were monads, composite monads, given by a distributive law. But yeah, I think that's where I'll leave it. Thank you.
Thanks very much. So I see there's a few questions, so go ahead in front.
Well, the spectrum of the product ring is the stone face field. And is there a way to see this from some sort of like a junction square, because you have this stone space between this optical on the set, and then you have this product condition on the other side.
Yeah, I haven't thought about it that way, but it'd be interesting to see. Yeah, we talk about it later.
Go ahead.
So in the case of code-density monads, there's a nice description of the Gleisi category for a code-density monad that comes up in historical shape theory. I was wondering whether there's a nice description of the Gleisi category for a push-forward monad.
I'm not sure. That's definitely something I should look into. Thanks for the question.
I like to think of push-forward in a fiber setting where it is like partition key. So here, maybe I would think that you have the category cat, and above it you have the category of categories equal to the monad. So would that be an alternative person-to-party of your one you gave?
Yeah, it is. Yeah, that's exactly. In fact, that's the way that Street phrased it in the formal theory one. That's exactly as a co-Cartesian thing. Yeah.
Sorry, this may be a bit naive, but it's well known that monadic functors don't compose. So I wonder if you have one of these examples and you apply the push forward of the first functor, what would you get? It would be a candidate.
Yeah. Do I have any example of that? Probably can't think of it right now, but I think I might. I'll get back to you on that. Thanks.
You mentioned that you can build these monads via composition of distributive laws. Do you have an example where the distributive law is not an ISO?
So yes and no. The case of the power set monad, it's not really a distributive law. It's in a paper by Richard Garner that there is a weak distributive law between the ultrafilter and the push-forward monad. And here that is not an ISO. So
it's also not a distributive law.
It's not a distributive law, but it's just this is not the monad that you would get from a distributive law. So when I said distributive law, I guess I should have said a generalization of distributive law. But yeah, thanks for the question.
Do you ever look at the dual version for comonads?
I haven't yet, but that'll be interesting.
I remember that you can get from this paper of Garner about aliens, you can get the finite limit preserving comonad whose algebras are sheets on a space as I think constructed by the dual version. So I think there are lots of interesting versions for non-trivial examples of comonads as well that might be fun to look at.
Great.
All right, then let's thank our speaker again.